Hello everyone, today let's solve the problem number 543, diameter of the binary tree. So you can just go through the question and you can just try to understand the question with the example that they have given. So I'll just summarize the question so that it will be easier to understand. So what the question states here, we are given the root of the binary tree. Here you can clearly see we are given the root of the binary tree and we need to find the diameter of the binary tree. So when I say the diameter of the binary tree, the diameter of the binary tree is nothing but the longest path between any two nodes in the tree. This you need to understand. Diameter of the binary tree is nothing but the longest path between any two nodes in the tree. So important points to note here is, one is the path length is measured by the number of edges, not the nodes. How many number of nodes we have, that we are not measuring here. You can clearly see. Just give me a second here. So suppose we are considering diameter over here, right? So this is edge basically. This is edge and we are not counting the number of nodes here. So we are not counting number of nodes. Instead, we have to calculate the edge, right? So in this case, and one more thing here is the path may or may not pass through the root. That's what they have given here. In this case, 1, 2, 3, 4, 5 root they have given here. So this is, we have to calculate the edge right here. 1, 2 and 3. So the output is 3 here. You can clearly see. So for the next example, they have considered here root 1, 2. So this will be 1, 2. There is only one edge. So the diameter of this particular tree is 1. The output will be 1. In this case, it will be 3, right? So again, I'm telling we have to calculate the edges. We should not consider the nodes, right? So I hope the question is completely clear. So let's discuss the approach first, followed by this one. Let's discuss the edge cases one by one. Finally, let's write the code and discuss the complexities of the code that we have written. As usual, let's discuss the approach first. So let's discuss the approach step by step. I have just considered the example that they have given in the question, right? First step is here. We are going with the approach DFS here. That you have to keep in mind. The first step are nothing but a depth first search, right? So what is the key idea here? The first step is we have to find the left and right subtrees recursively. We are finding the left and right subtrees recursively. Find here, in case, find left subtree and right subtrees recursively. This will be the first step. So what will be the second step here? So after finding the left and right subtrees recursively, diameter at each node will be left height and right height. In this case, if we consider this one, so just give me a second here. This one is 1 left height, this one is 2. Here it is only 1. This one will be the third then. So here in this case, output that is what they have mentioned here, nothing but 3. This is left height and right height. So then third step is we have to update the maximum diameter found so far. Update maximum diameter found so far. And final step is after updating the maximum diameter that we have found so far, we have to return the height. Just return the height. We have to return the height, right? In this case, that's what we saw here. We have to return the height of the current node to the parent. Why we are returning the height of the current node to the parent? We have to carry on with the further calculations, right? So that is the reason we are returning the height of the current node to the parent. So this is the approach that we will be going with. Let's discuss the edge cases one by one very quickly and then finally write the code. So let's discuss the edge cases one by one. First edge case is here, tree with only one node. Suppose this one, when I say tree with only one node, root here will be given by 1. The output will be 1. Why the output will be 1 here? Because we don't have any edge out. We don't have any edge at all here. We have only root, that is 1. Everything will be null here, right? We don't have to consider this one. So the output will be 1 here in this case. This is for the condition tree with only one node. So this is for the condition tree with only one node, first edge case. So let's move on with the second edge case, nothing but tree with only 2 nodes. Suppose I'll just consider here root equals 1 comma 2 here. This will be 1 and 2. Suppose if you consider in this way. So here the edge we have only one edge, right? So the output will be 1 here. Sorry, this one basically the output has to be 0, right? Why did I write 1? Sorry, did I explain wrong? Here we have the root 1. We don't have any edge at all here in this case. So the output will be 0 here. So this is for the tree with only one node. Sorry if I have explained wrong for this one. And let's go on with the second one. So this is for the condition sorry, just give me a second here. Tree with exactly 2 nodes, right? So here we'll consider 1, 2. We have only one edge, so the output will be 1. This is for the condition tree with exactly 2 nodes. So let's move on with the third. So yeah, third edge case will be here tree with skewed structure. When I say tree with skewed structure, all the left or all right. I'll just consider here. It might be like this. Either it can be 1, 2, 3 like this. So we have 2 edges here or all the right. So here it can be in this way. 1, 2, 3. This is fine. Same thing here. 1, 2 here. So the output will be 2 here, right? In this case, for input, we are considering here. This is for the third edge case. So root equals 1, 2, 3. So tree with the skewed structure, all left or all right. Here the output will be 2 here as we saw, right? This is for the condition tree with skewed structure, all right or all left. This is fine. Let's move on with the next edge case. Fourth edge case, nothing but here. Sorry. Yeah, these 3 edge cases are fine. So that was the final edge case. Let me delete this one. No need of this one. Fourth one. So these are the 3 edge cases that we need to remember. First one was for tree with only one node. Second one was for tree with exactly 2 nodes. Third one was for tree with this one skewed structure. We considered we have already considered all right or all left. I thought of writing for the right, but we have already considered all right or all left in the same this thing, third edge case itself, right? So here just keep in mind these 3 edge cases. Now let's move on with the this one, writing the. So let's quickly write the code here. First, what we'll do, as we have discussed in the approach, let's consider the variable to store the maximum diameter that's been found here. I'll just give here max diameter. I'll just consider max d here. Initially, let's initialize this one with 0. Let's consider the helper function. We are going with the DFS approach, right? So I'll just give here let DFS, or let me consider function itself here. Function DFS. So let me pass the parameter node here. This is fine. We are just considering the helper function DFS here. First base case is if node is null, then we have to return height as 0, right? So if there is no node found at all, then we are returning 0. In this case, I'll just give here if not of node, then I'll just return 0. This is fine. Next step is we will recursively find the height of the left subtree, as well as will recursively find the height of the right subtree as well. We have discussed this one. So this will be let left equals DFS of so node dot left. This is for recursively finding the height of the left subtree. Same thing, let's do it for the right subtree as well. I'll just change this one here from left to right. This one also from node dot left to node dot right. Hope this is fine. Next step is we have to update the maximum diameter, right? That was the third step in the approach. After finding recursively finding the height of the left and right subtree, we have to update the maximum diameter and return the height of the node, right? How can we update the maximum diameter here? I'll just consider max d here. Math dot max of max d as well as left plus right. This is fine. And finally, we will write the, we'll return the height of this node. We can just return here math dot max of left comma right plus 1 because the indexing starts from 0 in the binary tree. This is fine. So what we have done here in this case, line number 10 and line number 12 here. Line number 10 is nothing but we are updating the maximum diameter. Here we are just returning the height of this particular node. And the final step is here. We have to start the DFS traversal from the root here. We know that this one from root we have to start the DFS traversal, right? So then after that we have to return the maximum diameter that's found. So let's start the DFS traversal from root. This one DFS of root, and this way we will write. In this way we articulate in the form of code. So next let's return the maximum diameter found. I'll just give here return max d. This is fine. Let me format the code once and let me hit the run button. So here left plus right. Okay, fine. I have given the capital R here. So let me hit the run button again. So yeah, now you can clearly see the sample test cases are getting passed. So this is working correctly. Let me hit the submit button now. So you can clearly see all the test cases are getting passed. So the code works absolutely correct. Let's quickly discuss time complexity and the space complexity of the code that we have written. So the approach that we are going here, the approach that we went with here is DFS or depth first search, that we know. So overall time complexity would be here big O of n here. Why the time complexity here is big O of n? Because we visit each node once. That leads to the time complexity here big O of n. And what would be the overall space complexity here? The overall space complexity would be big O of h. Why the space complexity is here big O of h? Because we are making use of the recursion. We know that the recursion stack takes big O of h space. H, while I say h is nothing but the height of the tree. This we know, h is nothing but the height of the tree, and for the balanced tree, h will be log n, right? So it would be big O of log n. For the skewed tree, h will be n. So the time complexity will be big O of n. So overall space complexity we can just consider here big O of h, nothing but the height of the tree here. I hope the solution is completely clear. For now, this is it. Thanks for watching, guys.